Okay, so we left off on Wednesday, and we said, the conclusion of Wednesday was that if we're going to pick a projection to maximize the amount of variance captured, the projection that we're going to pick is the eigenvector of the covariance matrix. Do you guys kind of recall this? This was our conclusion on Wednesday, right? So conclusion from Wednesday is that, if we want to pick a projection of the data that maximizes the variance we capture, we will use the eigenvectors of the covariance matrix. Okay, and so today I'm going to show you as kind of like a neat little application of this. Okay, here, wait, let me dim these lights here. Okay, so, we start with some matrix Y, okay? And what we're going to do is we will project this onto our basically our eigenvectors of the covariance matrix. We're going to project this onto our kind of the principal components dimensions, okay? Component directions here. Okay, and then so to kind of get our directions W, we said W is going to equal the eigenvectors of our covariance matrix C, where C is equal to the covariance matrix of the centered Y, right? So this is centered Y so that Y has means of zeros in each column, right? So okay, and so what we do is we're going to let me show you what I'm going to do is let me also upload a picture here. Where did it go? Okay, so here is create file resource. Okay, so here's a picture of, this is Audrey Hepburn from Breakfast at Tiffany's, okay? And this picture, we're going to treat this picture as a matrix, okay? And so let me see the dimensions here. So this is 634 by 791. There's 791 rows, 634 columns. Okay? So let me just, so here, I don't need to make it that big, okay? This is my matrix Y. I've got 791 rows, 634 columns, okay? And we're going to treat this as a data set with 634 dimensions, effectively, okay? We're going to treat each column as, basically, if we think of what an image is, it's just a value indicating how bright or dark that pixel is. Okay, so we will treat each column as a dimension. Okay, and so now we have 634 dimensions. Okay, and so what I'm going to do is I'm going to project this. I'm going to find W. Okay, so we will find W, and we will project Y onto W. So all I do is I just multiply my matrix Y and do matrix multiplication against W. W is kind of the eigenvectors of the covariance matrix, right? Okay, so what I'll need to do is first I will center Y. Okay, so kind of our steps. Step 1 will be to center Y, and then step 2 we will take the covariance matrix of Y. All right. What are the dimensions? If I've got 634 columns in Y, what is the dimensions of my covariance matrix? It's going to be 634 by 634, right? Because basically we're going to see how much each column of values vary with every other column of values. So I've got 634 by 634. This is going to be my covariance matrix of Y. And I don't know if we recall anything about eigenvectors, but when I calculate my eigenvectors of the covariance of Y, what are the dimensions they're going to be? We're going to have 634 eigenvectors, okay? And so it'll be 634 by 634. Each eigenvector will be one column, but because we're going to do the entire thing, we're going to have 634 of these eigenvectors, okay? So each eigenvector is 634 by 1, but I have 634 eigenvectors. Okay. And so here I can do some dimension reduction. Okay, or I can project Y onto W. Okay, so Y is 791 by 634. And I can do this onto the full W. If I use the full W, it would be 634 by 634, okay? But I can truncate W. I can say, you know what, I only want to use the first 50 eigenvectors, okay? Because recall what we do is the first one captures the most amount of variance, the next one will capture the second amount, and so on and so forth. And every additional eigenvector I add will capture less and less variance. Okay, so that the 634th is hardly capturing any variance at all in the data. But if there is some, it's capturing it. And so I can just say, well, maybe I only want the first 50. Okay, so we can truncate these eigenvectors. And we'll say maybe just use the first 50. Okay, and then so if I do that, my W matrix is going to be 634 by 50. Okay, and then so if I truncate this, if I project Y onto W, here I've got 791 by 634, and I'm going to multiply this by 634 by 50. Okay, and then so the resulting thing, my projection, will be 791 by 50. Okay, and so this is this matrix would be the first 50 principal components of Y. Okay? So this matrix contains first 50 principal components of Y. Okay? So effectively, I've thrown away, you know, I don't know, like 7/8 of my data or something like that. Okay? I've thrown away a large portion of my data, or maybe even more. I don't know. If I'm keeping 50 out of 634, I've thrown away 90% of the columns here. Okay? Is that okay? Well, we can try to reconstruct the original data using only this thing. Okay? So we can try to reconstruct this. So based on this, okay? So then you know, we can try to, quote, reconstruct the original data from our, you know, shrunk down version. Okay, let me, I'm going to call this, after I do y times w, I'm going to call this x, all right? And then so we'll go from x and we'll try to get back our y's, okay? And so what we'll do, so my x, the dimensions here are 791 by 50, right? Okay. So to kind of reconstruct it, I'm going to multiply this by the transpose of my w's. Okay. We're going to multiply this by the transpose of our w matrix. Okay. So the w was 634 by 50, you know, after I've cut it. So now when I transpose it, it's going to be 50 times 634. Okay, and so this is going to kind of be, I don't know what we should call this thing. It's not really our y, but we'll call it y star. Okay, so y star is back to our original, the correct dimensions, 791 by 634, okay? Obviously, though, we've lost some of the data, okay? But this is, you know, we have lost some of the data, okay? And then because y, the way we found our original y is we've subtracted the means, we should add back the column means back to y, okay? We will also need to add back the column means. Okay, I don't know if this makes sense to us, but basically, you know, we said what we were trying to do is we're trying to kind of reduce the dimensions of our original data, okay? And then once we've reduced it, okay, well that's great and all, but can we get back our original data, right? This is kind of what we're trying to do. So let's try this out in R, and I hope this will work. Let me see. Session, set working directory. Let me. 102B, and then I have all of my things in this folder. Okay. So if I'm going to use a library called Imager. Okay. So this is I load up library Imager. Okay, and then here I'm going to load up this this picture I have of Audrey. Okay. All right, and if we ask, and we use this this command load.image, and if we ask what are the dimensions of Audrey, it's going to say 634. So 634 by 791 by 1 by 3. It's kind of this crazy array. And what it is it's 634 pixels, that's the number of columns, by 791, that's the number of rows. We're going to have one frame, so it supports it as if you had a movie with multiple frames. You could have different ones. And then it also, each frame has 3 channels of red, green, and blue. Okay? If in a grayscale image, red, green, and blue all have the same intensity. Okay, and that's what makes it gray. And so so here I'm going to just take one of these channels. Okay, it doesn't matter. I'll just take the red one. It does, but because it's identical to the green and the blue. And so I'm just going to subset this image file, okay, or this image array, and I'm going to say, store as.array Audrey, and then we're just going to take, frame 1, first channel, and I'm going to transpose it so it looks like what we've got. Okay, so if I just say what's the head of Audrey here, I've got 634 columns, and it's just too much. Okay, and we can see my environment. I don't know if you can see. It takes up a lot of memory in R as this, okay, because each cell or each pixel is now represented by type double, okay, whereas in an image you have 256 levels and it's just it's a small integer value, okay, so here it's type double, and so just a black and white image, 634 by 791 pixels, takes up 3.8 megabytes in memory. Okay, and then one of the functions that come with Imager is kind of this plot, the ability to plot the image. Okay, so I'm going to have to take this matrix. Okay, so I can just say the dimensions of Audrey here. I'm going to take this matrix and I'm going to transpose it, because that's just kind of the way this thing does. Okay, so we just say as.c image. This is the kind of file that it works, and we're going to plot it. Okay, if I take off aspect equals 1, then the picture gets all bloated. So aspect equals 1 keeps the aspect ratio correct. Okay, and so here, I'm plotting out the image that we have pulled. Okay, and so this is the original image file that we have. 634 for columns. Okay, and so this is what we're going to do in principal components analysis. First, we're going to subtract the means. We're going to find the column means. Okay, so we've got 634. I'm going to just say, give me the column means here. Okay, and so we can just say, what's the length of Audrey means, and I've got 634 of these. Okay, and then we're going to subtract this from each column, right? And so if I wanted to do this just kind of in one line, I first transpose the Audrey matrix, and then I subtract off the column means, and then I transpose that back. Is that okay? And so here I get my centered matrix right here, odd underscore centered. All right, and then we can just double check to make sure that the column means are all equal, okay, to 0, and indeed we do that. If I just ask column means odd centered, it's gonna give me a whole bunch of things on the order of 10 to the negative 17 or 10 to the negative 18. Pretty much 0, but because of the limitations of our finite number system, it's not exactly 0, but close enough to 0. Okay, so I have my centered data matrix, Audrey centered, and we could even plot this. We could even plot as.image Audrey centered. Okay, and it still looks, I should transpose that. It still looks a lot like it. It's just, you can see it looks streaky because what it's done is it has subtracted the mean of the column from each column here. Okay, so you know, in darker columns, so if we compare this versus the original, you know, if this column of pixels is dark, it subtracts off a large amount. And so all we've done is we've just, you know, if we averaged each of these columns, we would get an average of 0, okay, which probably puts us right at gray. Okay, so now what I'm going to do is I'm going to find the covariance matrix of our centered Audrey data, okay? So I can say, you know, what are the dimensions of this thing? What are the dimensions of our covariance matrix? Oops. Okay, and it's 634 by 634, okay? And now I'm going to find the eigenvalues, okay? And I know we didn't really cover exactly how to find eigenvalues. I've linked some things on finding eigenvalues based from Khan Academy. And really, like, you might be able to find eigenvalues and eigenvectors for like a 2x2 matrix or maybe a 3x3 matrix. But much more than that, it's a nightmare to even try to do by hand. We would not do this. But a computer does it really quick. We just say eigen, okay? And it does that. It's done, okay? And when you ask for the structure of these eigenvalues, we have the values. There's 634 of them. And then the vectors is a matrix of 634 by 634, okay? And the values themselves tell us how much variance it has captured. So I can actually create a plot of 1 through 634 versus, I'll do Audrey eigen $values, okay? I'm going to do type equals L. Oops, what happened here? I have a double equals here, okay? Okay, and then so you can see the first eigenvalue captures a lot, and then quickly the amount of variance it captures drops off, okay? And it gets relatively flat. So, you know, we could try, you know, our eyes are pretty good at detecting differences, so we'll be able to see what this looks like, okay? But here I'm going to just keep the first 50 eigenvectors here, okay? And I'm going to call this PC50, kind of like our first principal components. I should call this principal component directions. It's only after we project it that we get the principal components, okay? And then so the dimensions of my first 50 will be 634 by 50 rather than 634 by 634. And then to project it, I'm going to just multiply my centered data onto those 50 principal component directions. Okay, and so here we go. Audrey projected. Now my projected data is 791 by 50. So if I look at this, the projected, it doesn't say, it no longer says large matrix now. Okay, okay. Now it's 791 by 50 rather than large matrix. Okay, so we've reduced kind of the amount of space that this thing takes up now. Okay, technically I have to keep both. I have to keep this thing, the projected data, and the principal component directions if I want to reconstruct my original data. Okay, so I have to keep these two matrices. Okay, and so to reconstruct this, okay, so here we could package this up and send this off. Just the projected data and the principal component directions, okay? Oh, and my the column means. So I would have to keep those 3 elements. But we can reconstruct the data using those 3 elements. I'm going to do Audrey projected and multiply it by the transpose of those 50 principal component directions, okay? And so Audrey reconstructed, now it forms the large matrix again, okay? And we can see, you know, the dimensions of this is back to 791 by 634. And then we want to add back the column means back onto this thing. So I'm going to transpose my reconstructed thing, add on the column means, and transpose that back. Okay, so this is the reconstructed thing after I've added this back up. Okay, so keep in mind this reconstructed version of Audrey is coming from 791 by 50 multiplied by 50 by 634. Okay, so again, I've just taken these two things, my projected data and my 50 principal component directions, and I've reconstructed kind of the original, what I can approximate of the original thing. Okay, and so let's see how this reconstructed image compares to the original thing. Okay, so when I reconstruct the image, this is what it looks like. This is with the first 50 principal components. I don't know if you can tell on the projection. Let me just compare it to the original data. So this is reconstructed, keeping only basically the first 50 columns. Over here, this is the original data with all 634. I don't know if you can tell. On my computer screen, it looks pretty good, but and then when I've thrown away pretty much 90% of those columns, you know, there is some degradation in image quality, but as far as what we've preserved, it's not so bad. It's not so bad, right? Okay, and so here, you know, I can kind of go through and maybe I'll just do a few of these by hand. Okay, we'll do. Let me just show you what happens if I keep only the first principal component. Okay, so if I keep only the first principal component, then here I'm going to have my projected data will just be the first eigenvector, and then so we'll do that, and then we'll reconstruct the data based on that first eigenvector, add back the column means, and then we'll plot this. Okay, so with only keeping just one principal component, this is what the picture looks like. Okay, so this doesn't look anything like what we originally had. I don't know if, you know, we look at this and we're like, okay, I can see how you've kept kind of the structure, that there was a bright white thing here, and there's white down here and darkness over here, but it doesn't look anything like it, right? So here, you know, if I keep two principal components and I reconstruct it, you know, it starts to add a little bit of structure into our image. So, and then keeping just the first three, you know, maybe a little bit more, and then suddenly, maybe around 10 or 12, we'll start to see some pictures here. Okay, so here now I'm keeping kind of the first 5, and I don't know if we recognize anything here. At 6, this is what it looks like. And then we start to see something that resembles possibly a face, okay, at 6 principal components. And then at 7, you know, just things get a little bit better and better and better as we keep more and more principal components. Okay, so this is at 9, here's 10. Okay, so this is keeping the first 10 principal components. Again, you know, we've thrown away all of the data, and the idea is with principal components analysis is we're keeping just kind of like the most important columns to kind of get back the original structure of the data. And so we can see with just keeping 10 out of the 634, we get something where I bet if you show this, someone could kind of identify this is Breakfast at Tiffany's, right? Because it is kind of an iconic image. Okay, I mean, it's not a good picture by any means, but it is impressive that just from keeping the first 10 principal components, we get something that resembles what we think it should look like. Okay, and so I wrote a little loop that kind of runs through a bunch of these, and I printed out the images that it produces. Okay, and so here this is with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then I started skipping up with 12, 14, 16, 18, and 20, this is what our pictures look like. And this is with 25, and with 30, 35, and the image just gets better and better as we keep more. So this is with 40 principal components. This is with 50, 70, 90. Here's at 120. And then at this point, this is with 150. We don't get very much gains. 150 versus 180 versus 210, 250, 300, 400, 500 principal components. It's hard to see if it's making any difference here. Okay, we can see how the picture starts to get worse as the quality goes down, but at a certain point, keeping these additional things versus even the original image itself doesn't seem to really make a visually noticeable difference as far as what we do. Okay, and so this is kind of what we can do with principal components analysis. Again, we've our original data, whatever dimensionality it has. Okay, we're trying to find a rotation of it that captures the maximum amount of variance. Okay, and a lot of times the entire structure of a complex data set can be, the large parts of the structure can be captured with just a few of these dimensions. Okay, now when it comes to an image, there's probably not a whole lot of meaning behind what a principal component represents. Okay, there's probably not, like, we had 634 kind of principal component directions. There's not going to be much interpretability behind these things. But if we go back to kind of this example of people in Congress, right, and we could have our original data, if we look at kind of our 434 members of Congress as our rows, or 435 congressional representatives, not members of Congress, but 435 representatives in the House of Representatives. Okay, I think 435. 435 representatives in Congress, and then we surveyed 40 political topics. Okay. Now, there might be some differences between, the representative from, I don't know, the Republican representative from the, 1st Congressional District of, Missouri versus the Republican representative from the, 10th Congressional District from, whatever, some other state, right? So maybe there are some differences. But maybe we can just capture maybe the first two principal component directions, and then what this might capture, the first dimension, I'm almost positive, will be kind of this left Democrat slash versus right Republican divide. Okay, and this is going to be the first dimension that captures the most amount of variance. Okay, after this dimension, after this first principal component dimension, then we could say, what's the second dimension that and this is kind of like, once we've accounted for this initial source of variation, what's kind of like another thing. And there may or may not be an interpretable thing, but it could be something like, among, maybe it could be, military hawkishness, I guess, if that's a word I can make up, and the idea of, because you'll have some, whether they are Republican or Democrat, you might have people who are more willing to intervene in foreign affairs militarily versus those who are not willing to intervene militarily in foreign affairs. Who knows? All right. I mean, this one I'm making up. Okay. And it may not necessarily be this, but it might point to certain things that, like, some of these questions that we asked, being like, how do you feel about military intervention in this, in Syria or whatever it is, there might be certain questions that add further variance that we can see, okay? So I should just say sometimes the principal components directions can give us insight into the underlying structure, and then other times it does not, okay? And then sometimes no. Because, as far as an image goes, do these principal components mean anything? If we compare the first my first principal component, what is this doing? It's all of these principal components are trying to capture the difference between light and dark in the data, and but as far as the light and dark that was captured here, there's not a whole lot to say, okay? But as we increase this, we get a little bit. We can see how adding additional principal components adds structure back into the image that we have we're parsing down in the beginning, okay? And so this is kind of one of the applications. I'm debating how much more I want to spend on principal components analysis versus some of the other topics in the textbook. So I'll decide that over the weekend, and then we'll come back on Monday and take a look at this. Okay, but I thought this was kind of a neat little thing that we can do with PCA to see it. Okay, we'll end there, and we'll see you guys on Monday.